Hey, what's up everyone? Welcome to this live stream where we're going to cover how to get started with the composable architecture. So it's been actually quite some time since I wanted to talk about the composable architecture, or TCA as it is very often abbreviated, and as I will abbreviate it during this live stream just to save time. But there was one reason why I couldn't really make a training course about TCA. It's that even though I've followed the evolution of this architecture, I've seen talks about it, I've seen lots of code example on Twitter, on blogs, I've never used it myself. And I didn't felt like it was a good idea to give a training course about something that you've not used yourself, especially if you've not used it in production, especially for something that requires a strong commit from a developer, like the choice of an architecture does. But then a few weeks ago, I found a web page that you can see just behind me. So this tutorial made by the creators of the composable architecture, where they offer an in-depth tutorial on how to get started. And when I saw it, I figured that could be a good angle because I can do a live stream where I follow this tutorial. And so I discover the composable architecture, even though I know it a bit, but I discover it in depth and I can react to it. I can comment it. I can give my opinion as an experienced iOS developer. And I figured this approach was pretty interesting. So I was like, okay, let's do it. Let's do this live stream. So I see you are currently 42 watching live, which I think is the record on the channel. So I guess I was right in the idea that the topic of the composable architecture is definitely something that people want to learn about. So let me look at the chat because I see messages also in the chat. So I see you saying it's your first time joining the live stream. Welcome. I hope you will enjoy. Kevin Kelvin is saying, hey Vincent, looking forward to this. I hope I will be able to make TCA easy. Hello, William. Welcome to this live stream also. So thank you all for being here. If you are watching live, please don't hesitate to ask any question you have, make any remarks that you have. The chat is here for that, and I will do my best to try and answer your questions, your remark. If you want to follow along, I've put the link of the tutorial, so the page that is like behind me. You have the link in the description so that you can browse it. So let's see what we're going to talk about. I need to move the windows a bit on my end. Okay, I'm good. So this tutorial is called Meet the Composable Architecture, and as you can see, it's split into two parts. The first chapter is about the essentials, so exploring the basics of creating a new feature in the composable architecture, layering on side effects, and writing a complete test suite for the feature. So we're going to focus mostly on this today. As you can see, it should take, according to the time estimates, around 2 hours to cover everything. And then there is a second chapter about navigation. We'll see for this one. My goal is to not go over 2 or 2.5 hours for this live stream because then it starts to get a bit long, both for people watching but also for me, actually. So there is a good chance that chapter 2 will be in the second part. So let's get started actually with chapter 1. So let me just check that I don't miss any messages in the chat. I see David saying hello. Hello, David. William, you share the live stream in the Point Free community Slack community. That's very nice of you. Thank you. And I saw that the creators of TCA, so the two people behind Point Free, and of course, since I'm live, I've forgotten their name. I know that Brandon and Stephen. That's their name. So I saw they also shared it, which is really amazing. Okay, everyone is like, it's not gonna be anything but great. So much pressure. All right, let's get started. So we start with chapter 1, your first feature. So we're gonna learn how to create our first feature. And since I followed a bit TCA, I can tell you that feature, it's kind of like a unit of software in TCA. You can kind of understand it as like a module, maybe. But it's kind of like everything you need to have something in your app. So it would be maybe together like a screen, the logic with it, the test. We'll see if my definition is correct, but that's how I'm understanding it. So we're going to learn how to create a reducer, and we'll see that this word reducer is really important. If you've ever heard about reducer-based architectures, because TCA did not invent this, this might ring a bell. If you've heard, for instance, of architectures like Redux, that I don't know if it's still popular these days, but I know it used to be popular in the JavaScript world. This seems to be the same idea here. So how to create a reducer to implement the logic and behavior of a feature. Interestingly, we can see that they separate logic and behavior. I'm not sure where they draw the line, but it's going to be interesting to discover it. And then learn how to hook up that feature to a SwiftUI view. So 20 minutes estimated time. Let's get started. So section 1, creating a reducer. So the fundamental unit that features are built with in the composable architecture is the reducer macro and reducer protocol. So we can see that the version of TCA we're using uses macros. TCA, from what I understand, has been updated during the summer to be able to accommodate macros. And from what I understand, it has managed to reduce a lot the boilerplate you had to write before. And from what I understand, there is even better stuff coming soon. So, reducer macro and reducer protocol. A conformance to that protocol represents the logic and behavior for a feature in your application. This includes how to evolve the current state to the next state when an action is sent into the system, and how effects communicate with the outside world and feed data back into the system. So in this paragraph, we see already some of the core ideas of TCA. The idea of TCA, and just like any other Redux-based, reducer-based architecture, is that you have a data structure that represents the state of your app at a given point of time. And from that state, you can derive everything that is displayed on the screen. You should be able to render your app entirely using that state. And then when an action is sent, so the action could be something like the user tapping on a button or writing something using the keyboard, or maybe an event from the system happening, like a notification has been received, then this action is going to be applied along with the current state, and the two, so the current state and the action, will be combined in order to produce a new state that will evolve the state of the app, and so maybe will change what is displayed on the screen, this kind of thing. And we have effects that, from what I understand, allow us to encapsulate side effects. So it could be something as simple as, I guess, writing something on the screen, because writing something on the UI is a side effect, or sending a network request. But basically, you can understand a side effect as something that is going to change the outside world. So you send the network request, you've changed the outside world. You are writing on the UI, on the GPU, you have also changed the outside world. So that's how I would put this, this barrier between what is the state of the app and what are the side effects that a state and action can trigger. And most importantly, the feature's core logic and behavior can be built in full isolation with no mention of a SwiftUI view, which makes it easier to develop in isolation, easier to reuse, and easier to test. And from what I understand, this is kind of like the big selling point of TCA. So it's an idea that is kind of similar to the clean code idea, that your code should, like your logic, should be completely independent of your presentation framework, which, if you've seen the code samples from Apple and even the way they've designed some frameworks like Core Data or Swift Data, it's not necessarily designed around this idea, but it's one of the goals of TCA because it makes reuse and testing way easier. So let's start by creating a simple reducer that encapsulates the logic of a counter. We will add more interesting behavior to the feature, but let's start simple for now. So before I start to write the code, I need to create an Excel project because I want to write the code and run it as the tutorial goes on. So I'm going to create an Xcode project, and this way you can also create it if you're following along. So I'm creating an iOS app, and I'm creating a SwiftUI app. From what I understand is that you can also use TCA with UIKit, but the tutorial shows it in SwiftUI, so I'm going to go with SwiftUI, and I'm going to call it Getting Started with TCA. That's way too long of a name for an Xcode project, but it's too late, I've already written it. And I'm going to include tests because maybe we will be writing tests a bit later and it will save me from creating the targets manually. All right, creating the project. Okay, so we have this new project. And if I go back to the tutorial, you can see that we need, the first thing is to create a file and import the composable architecture. This means I need to add the Swift package to my Xcode project. So the way to do it is that you go to the repo of the composable architecture on GitHub. So I've put also the link in the description, but to get it, you can just do, if you want, you can just do, you search for GitHub and TCA or GitHub, the composable architecture, and you will find it. I'm going to copy the URL of the GitHub page. Then I'm in Xcode. So I click on my project. I select my project here. I go into package dependencies. I click on plus. I'm going to paste so the URL of the GitHub repo. So you can see I have Swift composable architecture, and I'm going to do add package. So you can see it's taking a bit of time to fetch everything because it's quite a big package, especially since it comes with macros. It needs to also fetch, for instance, Swift syntax. So actually, I haven't fetched it on this computer. I fetched it when I tested things before the live, but on another computer. So you can see in real time how long it takes to fetch it. I'm going to add the package to the target. So for now, I add it to my app target. And all right, I've added everything. I'm going to build my project once because I want to show you these errors. So I have 3 errors that happen because there are a few targets which are macros, and macros, if you've ever used them, you know that you need to trust and enable them when they've been fetched from the internet. It's like a little security measure that was added, I guess, because macros, they change your source code, and it's a way to avoid someone like putting I don't know, like some kind of malicious macro into your project without you being able to know about it. So I've enabled all 3. I've trusted and enabled all 3 macro projects, and you can see it's building. So you can see first time it takes a bit of time to build. I think it's mostly because of Swift syntax, but there are also like a few packages to build. So while it's building, let's go back to the tutorial. And so we can see step 1, we need to create a new Swift file named counterfeature.swift and import the composable architecture. And you can see in the note, they say that you will need to import it. And so they give you a link on the steps on how to do the import, which I've just done. So let's go ahead. I'm going to create this new file. It's going to be a Swift file, and I'm calling it counterfeature. Okay. And they ask me to import the composable architecture like this. All right. Let's try and build just to make sure that everything builds correctly. Build succeed. I think it's appearing outside of the part of the screen that I'm capturing, but the build has succeeded. So I can go back to the tutorial. So what's step 2? We're going to define a new struct called counterfeature and annotate it with the @reducer macro. And they tell us that the reducer macro does a few things for you, but at this point, you only need to know that it extends your type to conform to the reducer protocol. I think we're going to explore a bit and have a look at this reducer protocol. So I need to create a struct. How do I need to call it again? Counterfeature. All right. So I'm calling it counterfeature. It's empty for now. And I annotate with @reducer. All right. Let's have a look at this reducer protocol first. So this reducer, we can see it has 2 associated types, the state and the action, which makes sense with what we've read from the tutorial so far, in the sense that the tutorial takes the state at a point in time plus an action and generates a new state using the pair of the state and the action. Okay, we can see things about like a body. Maybe we'll see what it's about. And we can see here, so the reduce, which takes a state and an action and produces an effect of that action. So the side effect, from what I understand, produced by the state and the action. And apparently, that's the only thing within this protocol. And we can see there is a body here, and the body is a reducer builder of state and action. And I guess this reducer builder is some kind of syntax helper that will help us maybe write like the logic with some kind of domain-specific language. We'll see. So let's try and see what happens if I expand the macro. So you can see for now, it just generates the conformance of the counter feature, so the struct I've declared, to the reducer protocol. That's the only thing it does for now, but if you never use macro, you want to know here that a macro can have more than one role. So here is the role that make it that allows it to add a protocol conformance that is executed, but it might be possible that there are other roles for the macro that will be triggered as we add more code to the body of the struct. We'll see. So I go back to the tutorial. I just saw a message, just do the import, Xcode will help you. It's very possible that we will have some nice autocomplete also to help us. Here I'm trying to really like go in depth to try and cover everything, but it's possible that Xcode will be able to help you and you won't need to do like the expand that I've did when you're just writing a feature. So to conform to reducer, you will start with a domain modeling exercise. You will create a state type that holds the state your feature needs to do its job, typically a struct. Then you will create an action type that holds all the actions the user can perform in the feature, typically an enum. So the state, it lets you represent what's the current state of the feature. So basically everything that's needed to display the feature on the screen, for instance, even though it might be more than that. And then the action, you could see it as all of the commands that can be sent to your feature. So here the action, since it's a counter, will probably be like increment and decrement, but you could also have an action like reset to 0, for instance. I think they will show us the increment and decrement, and maybe we will try to do like the reset to 0 as an exercise. We'll see. But for now, let's just create the first struct, which is going to be the state, and then the enum, which will be the action. We'll see if the macro expands. You can see that now it adds the case pathable macro to the enum action. So the reducer macro is doing indeed more than one thing. Okay, let's go back to tutorial. So step 4, for the purpose of a simple counter feature, the state consists of just a single integer, the current count, and the actions consist of tapping buttons to either increment or decrement the count. And I would even say that they say button tap. That's interesting that they choose to say button tapped, because by saying button tapped, they kind of link incrementing with a button being tapped. But I would have expected to just have increment and decrement, because it could be triggered by other things than a button. So it's an interesting choice in the name. We'll see like if there are other conventions like this. So let's do it. So I'm adding the property count with a default value of 0 in the state. And in the enum, I had 2 cases. So how are they named again? Decrement button tapped with 2 P's. Perfect. And increment button tapped. Okay. We have some things regarding the naming in the tip. So it is best to name the action cases after literally what the user does in the UI, such as increment button tapped, rather than what logic you want to perform, such as increment count. That's very interesting. Personally, if I hadn't seen it, I would have gone the other way, but I guess it makes sense, because if you call it increment count, maybe first it can become like very confusing, because let's imagine that you need to update more than one property in the state. Are you going to list all of them? So I understand the logic that the action that the action has a unique source. It will be either a button tapped, a timer that finishes, a network call that returns this kind of thing. Whereas the changes to the state could be multiple. So I guess it's more descriptive. It's better to write a descriptive name. It's easier to write a descriptive name when you know that there will be a unique source than when there could be several consequences. So it kind of makes sense. I see a few remarks in the chat. Does TCA work well with the AppIntense framework? That's a very good question. A question that is way more advanced given my current understanding of TCA. But they claim in the README of the GitHub repo that it's supposed to work with most Apple platforms. So I guess maybe it will work, but you will need maybe to write like some helpers to make it work correctly. But I would say I would expect TCA to be able to handle deep links. And in a way, I guess AppIntense in their general idea are not that different than deep links in the way that they allow you to to have a custom entry point into your app, if I understand correctly what an AppIntense is. So I would tend to say that you can do it. Maybe you will not have the best ergonomics, but I would tend to say that you should be able to do it. Josh, you're saying, I find the tapped part of the name helpful. Obviously, a rename would be appropriate if increment tap can happen a different way. Exactly. But it also begs the question, if it can happen a different way, maybe we should have two different actions that just map to the same code. But maybe, in that case, you should have two different actions. That's how I would understand this convention. Oh, I see we have Stephen in the chat, who is one of the creators of TCA. And so you're saying exactly, it also means your logic can evolve to do more and not get out of sync with the action name. So I'm glad to see that I understood it correctly. Ryan, you're saying it can also mean that, for example, if there are two listeners listening to the action, for instance, a tracker would track the action of tapping the button, and the class responsible for increasing the count would increase the count upon receiving this increased button tapped. So yes, I agree with you that there is this idea of separating the action and then the consequences of the action. And thinking about it, I think the idea of having one action per thing that can happen, that can I was about to say to have one action per action. You very easily get into a circular definition, but to have one action for each different event, for lack of a better word, that can change the state of your app is nice, because this way it gives you an exhaustive list of everything that can happen. Like, you look at the enum action, you get an exhaustive list of everything that can happen to your feature. And I think that's good because it gives you a nice documentation. And since this documentation is written in code, you are guaranteed that it will always be in sync. So I think it's a good practice the more I think about it. So step 5, and finally, to finish conforming to reducer, you must implement a body property with a reducer that evolves the state from its current value to the next value given a user action. So we have this idea of combining current state and action to next state, and returns any effects that the feature wants to execute in the outside world. So we also return the side effects. This almost always begins by switching on the incoming action to determine what logic you need to perform, and the state is provided as in-out so you can perform mutations on it directly. As I started to read this part, I was thinking I have missed this when I showed you the protocol reducer, because if we go back to it, where is it? It's here. I have completely missed the fact that state is in-out, because when I showed you that it returned an effect, I was kind of thinking, I don't know if I saw it out loud, but I was like, where is the next state? And actually there is no next state. You are changing it in place with the in-out, the fact that the argument is in-out, which maybe there is also interest in terms of performance if the state is really big. Even though, no, because I think in-out, Swift still makes a copy. Just it kind of hides it, but it does make a copy. It's not really passing by reference. It makes a copy that it then copies back at the end of the function. But at least that explains how the change is made. So the state will be modified inside the reduce function, And additionally, the function will return effects that will trigger side effects. Okay, let's get back to it. And a note before I write the code. So a reducer is implemented by providing a body property and then listing the reducers inside that you want to compose. Right now, we only have one reducer we want to run, and so a simple reduce that you can see here is sufficient. But it is more typical to compose many reducers together, and it will be shown later in the tutorial. Perfect. Because for now, I have a hard time picturing how it will look like, but that makes sense because it's a complex topic. So I'm going to copy and paste because I will not remember everything after just glancing at it. Okay, I've pasted the code. So we can see first some inspiration being taken from SwiftUI by this use of the term body. We can see that even the fact that there is an opaque type, so with some, it kind of serves the same purpose. And so we have a reducer of self. Let's see what a reducer of is. It's just a type alias where you give it a reducer and you give the type alias a reducer R, and from this, okay, you give it a type that conforms to reducer, and it gives you a reducer of the state and the action. So it seems to be sugar syntax. This way we can write self and not self.state, self.action. So it's purely sugar syntax. What's interesting is that it's a type alias with a generic argument and a generic constraint, and it was exactly the topic of my. Sorry, I'm realizing that I'm covering the code. That's better. And I'm realizing it was the topic of my video this week, that type alias can handle generic arguments. So you have a great real-world example of it right here. So let's get back to the code. So we have this body, and in the body we have a reduce. We can see that it's very reminiscent once again of SwiftUI because the syntax is kind of similar to having, for instance, an H stack inside the body. And so we have this reduce that takes the state, the action, and we are switching on the action. And then in each case, we're going to write the appropriate logic, which I guess is going to be incrementing or decrementing the counter on state. Maybe I'm getting ahead of myself, but I have a good feeling it's going to be that. So let's see. Step 6, the logic for this feature is quite simple. We just want to either subtract 1 or add 1 to the state's count. We must also return a value of effect that represents the effect to be executed in the outside world. But in this case, we do not need to execute anything. So we can return a special value, a special non-value to represent we have no effects to execute. So let's implement it. So here is going to be, interestingly, so okay, no, it's state.count. I thought I read self, but it was a mistake. What would happen if I wrote self? I guess I would have, no, actually there is no self.state because it's a good thing I make this mistake because it leads me to an interesting point, is that there is no self.state. You can see that the state is not stored anywhere inside the feature for now. And I have a feeling that we're not going to store it. It's going to be maintained for us, but we're not going to store it. And that's an important point in the sense that it shows how, I guess, TCA is managing state for us. So state dot count minus equal 1, and here state dot count plus equal 1. Okay, and we are using the fact that state is in out in order to modify it, to mutate it. And then we have to return none for the effect. And I'm just going to add, trying to make it in a way that it looks pretty. Return none. Okay, let's just have a look at what is inside none. So we have an extension of effect, and it's basically an effect with an operation which is none, and the operation could be either none, so nothing to do, a task to run, or a publisher. So it seems that it's using either combine or concurrency under the hood. I won't go further because I guess we're going to cover effects a little bit later in the tutorial. Let me also check the chat. So Pratamesh, you're saying, I think reducer composition will be achieved by changing the generic type of the reducer body, which would make sense. I'm looking forward to when we'll get to it because this is really interesting. Okay, let me go back to Safari. So that is all it takes to implement a very basic feature in the composable architecture. There is of course a lot more to know about there is of course a lot more to know about, such as executing effects and feeding data back into the system using dependencies in reducers, composing multiple reducers together, and a lot more. But we will stop here for this feature right now and move on to the view. Okay. I'm thinking, do we try to implement the case? Yeah, let's implement it, the case where we reset it, just so that we can do it. And we will add the reset button afterward. So if I wanted to do it, I would add a case here. So remember, we call the action by what triggered it. So it's going to be a reset button tapped, because I will add a button in my UI that will be called reset. Then I need to add a new case into my enum. Interestingly, you can see that since a switch must be exhaustive, when I added a new case, I got a compilation error. So it's not possible to add an action that is not handled by the switch, or rather, not until you use default. And I guess it's a bad practice to use default in that case, because then you disable this safety that if you add a new action, the compiler will let you know if you have not handled it in all the places that you should handle it. And so I'm gonna call it reset button tapped, and this time it's going to be state.count equal 0, and we still return no effect. Does it build? Yes, it builds. All right. Let's go back to what the tutorial has in store for us. So section 2 is integrating with SwiftUI. Now that we have a simple feature built as a reducer, we need to figure out how to power a SwiftUI view from that feature. Because remember, up until now, our feature is living in complete isolation from SwiftUI. It can be deceiving, the fact that some of the naming convention does look like SwiftUI, but if you look at the import, you can see that SwiftUI is imported nowhere, so this file is completely independent from SwiftUI. So this involves two new concepts: store, which represents the runtime of the feature. So where is this struct stored? It's stored in the store, as the name suggests. And view store, which represents the observation of the runtime. So the store is going to hold the state, and the view store is going to let the views observe the state through the store, I guess, and be notified whenever something changes in the store. So I think we're going to see things that are quite similar, in at least conceptually, as the add state in SwiftUI, that also allows the view to be notified when state changes. So this time it seems we are importing SwiftUI now in counter feature. So it is our personal preference to keep the reducer and view in the same file until it is untenable. That's a very interesting choice. But others prefer to split the types into their own files. It's a good thing that they make their point, because I was about to create a new file. So for this tutorial, we will continue putting everything in counterfeature.swift, and we will now import SwiftUI and get a basic view into place. So we are now going to import SwiftUI into the file. So I'm glad that I did this little focus on the fact that up until now we were independent from SwiftUI, because now we're going to import it. And I guess it makes sense, like if you have a simple view, you define it in the same file, and then as it grows, you separate it. When we write a view model, for instance, we tend to write it into a separate file by default, because we know it will grow quite a lot. But I guess it makes sense if both are simple. So Stefan, you are saying now that ViewStore is a concept that is going away soon with Swift new observation framework. Yes, I've been made aware that it's going to be changing soon. Hopefully you will write a new tutorial, and maybe I will cover it. When I see that we still have 40 people watching, I think that it might be an interesting topic for me to cover. But yes, so that's a very good point, because as we've seen the macro at reducer, we see that it already generates boilerplate for us, and there is something even better that is coming soon that should make it even easier to use TCA. And I see that Ryan, you were saying the exact same thing in the chat. So good, good synchronization between the two of you. Good question. How is the initial state determined? What happens if you remove the count assignment to 0 in the state definition? That's a great question. And I think that for now, the default state is determined through this initial value. But we'll see if there is a specific syntax to deal with more complex situations. So let's get started. So let's import SwiftUI in the file, and let's add this counter view. So let's import SwiftUI, and just below the counter feature, I'm going to add the counter view like this. Okay, step 1 is done. Step 2, the first thing one adds to the view is a store that is generic over the reducer we constructed in the previous section. The store represents the runtime of your feature. That is, it is the object that can process actions in order to update state and can execute effects and feed data from those effects back into the system. So the keyword here is definitely runtime. The store can be held onto as a let. It does not need to be observed by the view. So I guess the store is a reference type, if we can declare it as a let, which would make sense for it to be a reference type, because it's kind of like following the same logic than SwiftUI, where views are structs, but data objects tend to be reference types. So let's add this store. So it's going to be a store of counter feature. So let's going to just reindent the code. Perfect. So let store equal store of and counter feature. So it's a store that stores the counter feature we've defined just above. Did I miss something? Oh, it's not. It's just a type like this. And I guess I will need to pass it through the init of the view then. So let's look at store of. So it takes a reducer, and that's interesting because it takes a reducer, and remember that our feature conforms to reducer. So I had a bit of a hard time like wrapping my head around it as I was like covering the last couple of steps. So when we say a reducer, a feature is a reducer. So it's a store of the feature, and it's a type alias. So once again, this convenience type alias that just accesses the two sub generic types. And the store, so it's a class, it's indeed a reference type. We have some buffered actions. I guess it's something to deal with maybe with back pressure, some logic of caching, some logic of children, which can be interesting, because if you've used SwiftUI before iOS 17, you might know that observable objects cannot have children, in the sense that a change in a sub observable object would not be relayed by the parent observable object. Here it seems that it might be possible, but we'll see. So we have the effects that are also managed. Okay. And the reducer. And so the reducer, I guess, is going to be it's just going to be our feature. All right. Let's get back to the tutorial. We are at step 3, and it's when we start to implement a view. We can see how it's going to look like. So next, we can implement some basic view hierarchy for displaying the count and providing buttons for incrementing and decrementing. And in my case, also resetting, because I decided to add myself this extra case. And a note, you can read state from a store directly. No, you cannot. You cannot. You cannot read state from a store directly, nor can you send actions to it directly. So for now, we'll provide stubs for that behavior, but once a view store is added, we can provide the real implementation. So remember, It's what was said in the intro of this section. There is an intermediary between the store and the view, which is conveniently named view store. So I'm just going to copy and paste because I don't want to write all of this SwiftUI code by hand, and I don't think it's super interesting for me to do so. So we can see in the body, we have a text that is going to display the value of the counter. You can see that for now, it's not hooked up to the counter. It's only to the counter to the feature. I mean, to the counter in the feature. It displays a static text. Same thing for the button. It doesn't have anything in its action. I'm just gonna run it in the simulator, just in case, if there is a compilation error, we can catch it early. So showing you the simulator. I will also put it into dark mode because I don't want to have a big white thing that's going to illuminate me a lot. So it's still launching. Still launching. We have the hello world. Why? Because I need to go here at the app level and instead replace the content view with a counter view that will then ask me for a store. So actually, I will go back to the tutorial because there are a few steps I need to follow before I can actually launch the app. But this is what the view will look like once I will have made the app build. Okay, so with some basic scaffolding in place, we can now start actually observing state in the store. This is done by constructing a view store, and for SwiftUI views, there is a convenient view called view with store that provides a lightweight syntax for constructing a view with store. So let's see how we are going to use this. So step 4, view stores requires that state be equatable, so we must do that first. Once the view store is constructed, we can access the feature state and send it actions when the user taps on button. So I'm looking to see, it's not explained in the tip. Actually, when I went over the page before the live stream, I wondered why we make state equatable only like at that point. And why don't we make it equatable here, for instance? If you're still watching, Stefan, if you have the answer, I would be super curious to know it. But let me go back to the change I need to make. So I need to write an extension of counter feature.state to make it equatable. So I'm going to do it here. And this seems to suggest that this should have its place in the view. And I get this error. State is not, let me scroll so you can see it. State is not a member type of struct getting started with TCA.counter feature. Even though there is a state here. I get this error circular reference attached to macro. So actually, yes, that's why I wondered why we were doing this, because when I tried to do it, I had a compilation error, and the way I solved it was by doing this. So I'm going to do this for now. If it's wrong for some reason, please let me know, but it's the way I found to solve this compilation error. What does the tip say? Currently, okay, so the tip is for after we've written the rest of the code. So we can see as we are wrapping our VStack into a view with store. And so a view with store, it's a view that takes arguments and then makes it available through its closure. So it's kind of like a pattern that is a bit similar to a geometry reader in a way, even though like they do very different things, but they have this pattern of they provide you a way to interact with something through an object that they pass to a closure. So that's where there is this similarity. So Stefan, you're saying mainly the equitable conformance is delayed for progressive disclosure. In the next version, you can read state directly from the store, and equitable isn't needed until you test. So I guess it makes sense, like to delay like a conformance until it's needed. And it's true that yes, you need equatable in order to know if something has changed. So it makes sense in that case. And of course, for testing, if you want to test that the test that you get is the same as the one you expect, you also need equality. Okay, let me write so the change I need to make. So the text now. So first, I need to wrap my my view inside this view with store. So I'm gonna start writing it. So here I'm writing the view with store. So I pass it the store, and then this observe, which only returns $0. I guess this observe closure, maybe the tutorial will talk about it later, but I think it might be useful, like if your store stores many things and you only want to observe a sub part of it, like to observe only a specific property of the store. I guess it's for this, even though I'm not sure. So correct me if I'm wrong here. So then I need to select my entire VStack and move it inside the store. Perfect. While I'm at it, I'm also going to fix indentation. Okay. And so now here for the text, so I'm going to use string interpolation, and I'm going to do view store dot count. So let's see what is the type of view store. It's a view store of counter feature state, counter feature action. Okay, so I guess it's that because you can read the state and then you can send actions to it. So that makes sense. And I'm gonna try and see what is how is viewStore defined. So it's a class that is observable object. Okay, and I was wondering why I was able to get the count property on it directly, but I think I know why. Yes. So I'm gonna try and leave you like a bit of time to guess. So if you can guess why I can access the count property on the view store, which is a property of the state. So it should be normally like viewStore.state.count, but I can do directly viewStore.count. If you can guess the Swift feature that does it, it can be a nice challenge. My guess is that it's the feature that allows you to create a subscript, a dynamic member lookup subscript with key paths that allows you to basically like access all of the key paths of a sub property at the parent type level. I think it's that. So let's see if I was correct. So we have a bunch of inits. Trying to scroll a bit. So here we have the state, but yes, it's here. So it's here where we have this subscript that allows us basically to access the properties of the state directly on the view store itself. And it's a really great use case for this property, for this feature of Swift. Oh, Stefan, you're saying about the compilation error we saw. So the compiler error you saw is a Swift macro bug. So we ought to update the tutorial till Apple fixes it. Okay, I'm glad that I didn't miss something that was very obvious. And view stores observe closure can be used to prevent parent features from observing too much state. Luckily, we can remove this concept in the next version, though. So yes, I think I got it correctly. It's like if you want to scope your observation to only like a smaller part of the state. Okay, perfect. So now here I'm displaying the right data. And so in the button, I guess, I don't remember the code I need to write, but it should be pretty intuitive. I guess I will have a method send action. So send action, and the action I'm going to send is decrement button tapped. And now it's true that it makes sense when you see it like that to have the name send decrement button tapped. Because if it were to be called send counter decrease, you can see that in a way, the internal logic of the state is leaking into the view. So now that I see it, the naming convention makes even more sense. And so here, of course, it's obvious because it's the code is symmetrical. It's increment button tapped. Did I get it right? Let's check. Yes, it was indeed that. Okay, so we are almost ready to launch. We just need a way to actually store pass the store to the view when we build it. So it's what's happening here. So next, we want to actually run the feature. We will start with a preview. To do this, we construct a counter view, and to do that, we need to construct a store of counter feature. So it's what I was missing here in order to be able to run the app in the simulator. So stores can be constructed by providing the initial state you want the feature to begin in, which links to the question you had just before, Prathamesh, as well as a trading closure that specifies the reducer that powers the feature. So let's see There is no change to the code. Oh yes, yes, it's okay. It's the preview. It's the preview. I thought it was the app here, but no, it's just the preview. So I'm going to add the preview code here. We can see the preview is appearing. Okay, I'm trying to make it so that you can see it. So I'm going to fix the indentation so that it's easier to read, like that. So we create a counter view, and for the store, we create a store with an initial state, which is, so it's just building. I think since my project cannot build, it won't run the preview. So I will just put, I will just like comment this. And actually, I think in the tutorial, that's what, yeah, that's what you were doing in tutorial also. So I should have done it before. Okay. Does the project build now? Yes. And is the preview working? It's building. I guess it's a good thing that it's building. Yes, perfect. Okay, let's make it so that it fits the screen, and maybe let's put it in dark mode so that I don't destroy the eyes of people who are watching like in a dark environment. Okay, so when we click on plus, oh, I need to make the preview interactive. When we click on plus, the counter is incremented. When we click on minus, it gets decremented. Amazing. Okay, let's get back to the tutorial. So with that done, we can run the preview to see that tapping the plus and minus button does indeed change the visible count in the UI. And while we are at it, let's add the extra reset button that I decided we would also do. So I'm just going to reuse the code of the minus button. So this one is going to be called reset. And I just need to send the reset button tapped action. And normally that should be the only change I need to make. Maybe I need to save my file. How come I don't see the button? I think the preview didn't refresh correctly. I'm not crazy. I did add a reset button. Is it because it's in dark mode? No, there is no like. Huh. Just going to stop it and relaunch it. I guess the preview just like didn't get that I changed the code. Okay, now it's here. And so the reset button is working as expected. Perfect. Let's get back to the tutorial. So before moving on to the next section, let's quickly show off a superpower of the composable architecture. Because all of the features, logic, and behavior are contained in the reducer, we can run the preview with a completely different reducer to alter how it executes. That's interesting. So let's go back to where we build so the store. So here, what's interesting is that you can see that we give it the default state, which is the state struct defined inside the counter feature struct being initialized, but we also give it the counter feature for the reducer. So we could operate on the same state, but with a different behavior. And I guess that's what the tutorial wants to show us. So for example, in the preview, we can comment out the counter feature. So actually, it wasn't the code in the app that was commented out. Or was it? No, it was like, I thought it was something else. So it's this that I'm supposed to comment out. Okay. So as I've done, I've commented out the counter feature reducer, and the store will be given a reducer that performs no state mutation or effect. So it's kind of like a no-op reducer. It's a reducer that doesn't mutate state and doesn't emit any effect. And this allows us to preview the design of the feature without worrying about any of its logic or behavior. This means that we could define the state and then wait until we define the behavior and still be able to test the app. So that's interesting. Let's see how the preview looks like with this change. Okay, reset doesn't do anything, but that's not a good way to test it. Plus and minus also don't do anything. So that's interesting. I didn't know about this feature of TCA. And here it says, notice that the video demonstrates that tapping the button does not cause the count to increase or decrease. That is because we are using the empty reducer in the preview. Okay. Um, I see an interesting remark, which is that was a very complicated way of creating a counter. That's a good point in the sense that indeed there are simpler ways to create a simple counter in SwiftUI, but I guess it's going to make up for it when we see, for instance, how we can test that the counter works as expected. And also, I think it's this kind of situations where it's a toy example, so it's not like it's not as complex as a real world problem. However, you still need to set up a bit of infrastructure to run it. So what I mean to say is that a real world example will be more complex in the state, but it might not require much more code than what we've written in order to handle it. So the complexity might seem higher just because the state we are dealing with is overly simplified. But with a real state, maybe it's possible that this changes a bit. But as always with any kind of architecture, in the end, it's a matter of do you feel like you're going to enjoy working with this? Does it solve problem for you or not? If it does, go for it. If it doesn't, then use an alternate option. I don't think it's a good thing to be dogmatic when it comes to architecture. Um, Personally, the way I like to define architecture is that it's a way to organize code in order to solve business problems. So if you need to go very fast, iterate super fast, and maybe pivot your business every other week, this is probably not what you're looking. This is probably not what you're looking for. But if you need to have a code base that is super stable because you know you're going to work on it for the next 3, 4, 5 years with developers coming and leaving the team, maybe having this kind of strong foundation can be useful. A question outside the box. What's your thoughts about clean architecture design pattern? Not much because I don't know that much about it. About just like the idea of it that you should isolate the different parts of your app, but I've never used it that much. What I liked when I saw TCA for the first time is that it seemed to do um, the benefits, the main benefits of clean code, but without the crazy complexity. If you were doing iOS 4, 5 years in the past, maybe you remember an architecture pattern named Viper. I don't know if it still exists these days, but it was this very complex architecture that was based on clean code and that had a bit of popularity around 2016, 2017, that the pre-COVID era, basically. And many people, myself included, did not like it because it was a lot of boilerplate, but for real, like you had to create I don't know how many files just do something very simple. So I think clean code has its benefits, but I think you need to be pragmatic and not you don't want to get into a crazy architecture just for some hypothetical benefits that you might not even need. Uh, from what I see from TCA for now, it seems reasonable enough in the sense that what we've done doesn't seem that much more complex than writing a good view model in a SwiftUI view. But let's get going and let's see what's going to happen next. So that is all there is to implementing a basic feature in the composable architecture. The feature is of course very simple and doesn't involve anything interesting like side effects, which will be the topic of adding side effects. But before any of that, let's see how to integrate this feature into an application. Here, I would say we haven't implemented any complex side effects, but if you want to be very by the book, the fact that when we change the state, it updated the text, in a sense, it's a side effect. It's one that is not managed through the effects API, but technically, it's still a side effect that we've done this. Okay, so I guess we are moving to section 3, integrating into the app, because remember, we've not run the app for now. We've just used the preview. I still don't know how to run the app and store the store so it is accessible at the app level. So we have now integrated our composable architecture feature into a SwiftUI view, and we've been able to run it in the preview. Next, we need to figure out how to run the feature in the full application by altering its entry point. This will allow us to run the feature in a simulator or on a device. So now we have the entry point of the app, which is the app.swift file. So by default, the entry point of your application is probably a file called app.swift. That's what Xcode creates for you by default, and looks something like this code. So indeed, I'm going to go into this file. The name is just a bit longer. I call it Getting Started with TCA App, where they just call it My App, but it's the same idea. So we will change the entry point of the application so that it constructs a counter view and provides the store just as we did in the preview. So we need to import the composable architecture. And then, so we need to create our counter view and give it a store. And indeed, the code seems very similar than what we did in the preview. Fixing indentation. So we create the store initial state, which is the initializer generated by the compiler of counterFeature.state. And then we pass a counter feature for the reducer, so for the logic to be executed. So at this point, I should be able to run the app. Before I keep reading, I will just run the app, just in case I've made a mistake. It's good to catch it as early as possible. So the app is running, the logic is running, perfect. I can keep going. So I wanted to do this. Okay. So is it what I did? Yeah, I did step 2. So now step 3. It's important to note that the store that powers the application should only be created a single time. For most applications, it should be sufficient to create it directly in the window group at the root of the scene, so which is what I was doing here. I'm creating it inside the window group. But it can also be held as a static variable and then provided in the scene. So we're going to change the code to do that. So let's take the store, which is right here. So it's going to be static let store equal this. And then here is gonna be, so now I need to use the full name of the app. Getting started with TCA app.store. What's the type of store? You're asking, what's the type of store? So let's have a look. So store, it's a class. So that also has two generic arguments, state and action. So just like view store. And I think I think we went, either we went over it or it was view store and they were very similar. So, but that's the type of store. Is this final class? So that's not meant to be extended using inheritance. And you can see that from what we see here, we get the sense that it's meant to manage the state, to maintain the state, to keep track of the state, to deal with entering actions, and to produce effects, and to deal with the lifetime, to manage the lifetime of these effects, either through cancellables or from maybe other things that are used in the Swift concurrency API. But let's go back to the tutorial for now. So I've made the change. What do they say? They say that we can demonstrate another superpower of the composable architecture. We can demonstrate another superpower of the composable architecture. For context, it's past 9 p.m. when I'm doing this live stream in France, and you can see I'm starting to get a bit tired. So reducers have a method called underscore print changes. If you've done SwiftUI, this might ring a bell because SwiftUI has an equivalent method. And if you don't know about it, I have a video on my channel about it. That is similar to a tool that SwiftUI provides. I haven't read it, but it's always the same with this kind of video. I just say what the text is saying just after. So when used, it will print every action that the reducer processes to the console, and it will print how the state changed after processing the action. The method will also go through great lengths to collapse the state difference to a compact form, in the sense like letting you know what changed and not just doing a dump of the before and after, and your state has 60 properties and have fun finding what has changed. This includes not displaying nested state if it hasn't changed and not showing elements in collections that haven't changed. So let's do this. So update the entry point of the application to invoke underscore print changes on the reducer. And before I do it, I see you have a comment. You're saying, okay, so it can be subclass to tuck away the boilerplate. NBD, I'm not sure what it means. I'm not sure what it means. I'm trying to, yeah, I'm not sure. A static property can work. I'm sorry, I'm not sure what NBD means. And apparently there is a change in Xcode also for the underscore print changes. I'm also showing it so that people watching the replay can see it easily. Okay, so here I'm back at the entry point of the app. And so on the store or on the feature? I call it on the feature, not on the store, which I guess is nice because it can allow me to enable this only on a specific feature. So if I want to have console logs, it's better to be able to scope it so that you can only see what you want to see in the console. So let's try and see what happens now when I launch the app again. So let me make it so that you can see both the console and the simulator. Normally, you should be able to see everything. So I click on plus. We can see received action, counter feature action, increment button tapped. And then we can see, I guess the minus is the entry state and the plus is, I guess it's the change. So what was removed, or like the previous version was a count of 0 and the new version is a count of 1. Okay. So I guess minus means entering state and plus means exiting state. Which, if you think of it, like I'm thinking about in terms of like an electricity diagram where you would have like a plus and a minus. I don't know how you say it in English, but like on a battery, you have a plus end and a minus end, and power goes out of the plus and goes back into the minus. It's I guess it's a similar idea. The one thing that is very important to note is that it says minus and plus here, but it's not linked to the fact that we increment and decrement. That's what I wanted to highlight. It's just a coincidence that our actions are increment and decrement, and it says minus and plus here. Here, I think that minus says it's the entering state and plus the exiting state. Let's get back to the tutorial. So it says, now when you run the application in the simulator and tap the plus and minus button a few times, you should see logs printed to the console showing you exactly what is happening. It's exactly what we've been able to see. Okay, we've finished the first part, which was your first feature. Now we'll do adding side effects. And you're saying, Stephen, the plus and minus is because the format is a diff, so it's similar, for instance, to what you would see when you look a pull request on GitHub and you see minus for what has been removed and plus what has been added. And it makes sense. It's true that if you use a diffing algorithm to make the comparison, to follow this convention. And you're saying when your state has more fields, the plus minus will be formatted to just the properties that have changed, which seems like a really great feature. So next step is side effects. So how to return these effects that we can use in order to, for instance, make a network call. So let's go ahead. What's nice is that the first one was saying 20 minutes, and with the explanation it took 1 hour. So we'll see. Maybe we'll see just how far we can go. Adding side effects. So we're going to learn how to communicate with the outside world in our features and feed data from the outside back into the feature. So maybe we'll see a network call, I don't know, but it seems like the typical example of a network call where you are triggering the effect of making the call and then the call returns and it feeds data back into your app. So section 1, what is a side effect? Side effects are by far the most important aspect of feature development. They are what allow us to communicate with the outside world, such as making API requests, interacting with file systems, and performing time-based asynchrony. Without them, our applications could not do anything of real value to our users. However, side effects are also the most complex part of our features. State mutations are simple processes you run the reducer with the same piece of state and same action, you will always get the same result. It's a deterministic process. Unless, of course, if you have a random button that calls a random number. But then maybe that should be an action rather than just something you implement in your state. Because the idea is that it should be indeed deterministic. But effects are susceptible to the vagaries of the outside world, such as network connectivity, disk permissions, and more. Each time you run an effect, you can get back a completely different answer. Let's start by seeing why we can simply perform effectful work directly in our reducer conformances, and then we will see what tools the library provides for performing effects. Okay, so step 1. We see there's a new button. So what is it going to do? Let's add a new bit of functionality to the counter feature we built in your first feature. We will add a button that, when tapped, makes a network request to fetch a fact about the number that is currently displayed. So there are two ways you can approach this. Sometimes people like to work on the reducer first and then on the view. Others like to start with the view, which is what we will do now. We have added an additional button to the bottom of counter view, and when it is tapped, we will send a fact button tapped action, which does not yet exist in the counter domain, but will soon. So we are adding a new button to the view. So where is it added? Just to check, it's added after the H tag. So here we have this H tag right here, and after it, I add this button. Once again, let's fix the indentation, even on the whole file. Perfect. So the button fact sends this action, which does not exist yet. So for now, the code doesn't build. We will also add a progress view at the bottom to display while we are loading the fact. And we will unwrap a bit of optional state to display the fact. We are using the isLoading and fact state to accomplish this, neither of which exists in the counter feature, but will soon. So it's here. So we are adding some more views. So we are saying if view store is loading progress view, show a progress view. Else, if there is a fact in the view store, then display it. And if it's not loading and there is no fact, then we don't display anything. And these things are properties of the state. Remember, we can access it directly on the view store because there is this feature that lets us use the properties of view.state directly on view. No, there is the fact that instead of writing view.state.isLoading, we can write directly, I said view, no, it's view store. Instead of writing viewStore.state.isLoading, we can write directly viewStore.isLoading. I hope this time I said it correctly. But since we haven't implemented isLoading on the state, this code also doesn't build yet. Same thing here for the fact. So that is all it takes for the view. The code is not yet compiling because we are using state and actions that don't yet exist. So let's fix those errors in the reducer. So recall that this is what our counter feature reducer looks like so far, as built in your first feature, so the chapter just before. It has a simple state and action type, and the reducer simply decrements or increments the count state depending on which action is sent. In our case, it also resets the state. It also resets the counter, not the state. I mean, it also resets the state, but it resets the counter, and since the state is only made of the counter, we can also set it resets the state. So step 4, let's add the additional state and actions that have been dictated to us by the view. We know we need some fact and isLoading state, and we need a fact button tapped action. We can also implement that action in the reducer by flipping isLoading to true, and we'll clear the fact state when any button is tapped. And finally, we will return none, just like we did in all other cases. So let's do that. So here on the state, I add a property which is a fact, which is of type optional string, and so it has a default value of nil by default. And then a property is loading, which is Boolean, and it would make sense for it to have a value of false by default. That's indeed the case. And so what we do now is that whenever the count change, so that's interesting because we need to reset the fact manually whenever the count change. Maybe later in tutorial, maybe we'll see if there is a way to map the fact to only write it once. Like if the count changes, then we set the fact back to nil. We'll see if that happens or not. But I guess I need to do this so every time. Okay. And I need to also handle the new case, which is fact button tapped, which I also need to add first. So I need to add the new case first. So fact button tapped like this. Then I need to write the logic associated with it. And so what is it? So it's going to be that isLoading is now true. Okay. If there was already a fact, we put it to nil. All right. And for now, we return none. So we still return no side effects. So we haven't implemented a network call or anything like that yet. Now the question is, how can we perform a side effect? We will be using numbersapi.com to fetch a fact for the state's current count. We might hope we can just use URL session directly in the reducer to perform some async work. But unfortunately, that is not allowed. So namely, the reducer is synchronous, and so we can't call an async function inside of it. James, you're saying, isn't it Redux architecture? Indeed, there is a very strong similarity in with Redux architecture. If Stefan is still here, maybe he can talk to the finer points of the differences in the two architectures, but we could say that they are like relatives. I don't know how close relatives they are, but there is definitely like a strong similarity at play here. So the composable architecture separates the simple pure transformation of state from the complex, messy side effects. It is one of the core tenets of the library, and there are a lot of benefits to doing so. Luckily for us, the library gives us a tool that is appropriate for executing side effects. It is called Effect, and it is explored in the next section. Oh, so you're saying Redux plus Elm, so Elm to this way of modifying, so Redux plus Elm equal TCA, Elm being this this approach where you have like the state and the enum. I remember hearing about Elm and the Elm architecture, and but I always saw it as like the same thing than Redux. So yeah, I'm not knowledgeable enough to to make a good comment on that part. Do you use a store in composable architecture? Yes, you do use a store. We saw it just before, and I guess we'll see it soon again. Okay, so let's create this effect. So performing a network request. Now that we understand what a side effect is and why they cannot be performed directly in a reducer, let's see how to fix the code we wrote above. So actually, I'm going to write this bad code so that I can then modify it later and do just like the tutorial wants me to do. So it would be something like this, I guess. Do I get the error? I want to see if I get the error. I get an error that says cannot pass function. Okay. Yeah, I don't get the same error, but it's because like it's the async part. You can see that it's because it's async and throwing, and it's not expected to be async and throwing. And we can see we get some. It tells us that the issue comes from here. I see. So Stefan, you're saying, yep, we mentioned Redux and Elm as inspiration for TCA. TCA is kind of in the middle of the two, mainly in how it manages effects. Perfect. We're getting at effects. Okay. So maybe I already, I'm not sure. But now that we understand what a side effect is and why they cannot be performed directly in the reducer, let's see how to fix the code we wrote above. The composable architecture bakes the notion of effect directly into the definition of reducer. After a reducer processes an action by mutating state, it can return something called an effect, which represents an asynchronous unit that is run by the store. Effects are what can communicate with outside systems and then feed data from the outside back into the reducer. This is exactly what we want to do for our number fact effect. We want to make a network request, and then feed that information back into the reducer. So let's get started. Step 1, the primary way one constructs an effect is via the static method run priority operation catch file ID line. Hopefully, we will only provide some of these arguments. This provides you with an asynchronous context to perform any kind of work you want, as well as a handle for sending actions back into the system. So here it's in return.run. So actually we need to remove this code and we are no longer returning none. So remember, none, it was this. And now we are doing run, which is going to allow us to create a task, to have a task where we can write async code. And we can see we can do the same thing with a publisher if we want to use combine. Even though for a simple example like this, I think it's definitely a good thing to use Swift concurrency, so async await rather than combine. So we won't provide a priority. We will just provide this operation, which is a closure that takes a send action, so something where we can send back new actions and also do async stuff. So like that, I go back to my tutorial. And so here it's okay to do async work because the closure is async and we can send actions back into the system. So we have the send argument. That's the one I had forgotten. And so on it, we can do send and then I guess, yeah, it's call as function. So actually we will be passing the action like this. So once again, if you've never used call as function, I think I have a video on it on my channel. It's a nice feature of Swift that allows you to call an object, basically. So you can check out the video if you want. It's one of the very early videos, so hopefully you will see a big difference in quality with what I'm doing these days, but it does exist. Either it's a video I've done myself or it's one I've done with John Sandel back in the days. So let's see how we implement the network call. So trailing closure of the dot or run method is the perfect place to perform a network request to fetch data from the Numbers API and turn it into a string. So that's what I was saying. Unfortunately, Numbers API does not offer HTTPS, so you will need to add an entry to your application info playlist in order to allow HTTP requests. See this article for information on how to do that. I did not expect this, but let's do it. So how do I disable ATS? So I need to say this. So allow insecure load for WebView. No. I guess I need to add an NS exception domain. All keys in the ATS. So let's see. I need to change the playlist. Where is this thing? I don't think we have. Do we still get a playlist when we do an iOS Swift UI app? Because I don't have the playlist created. I'm just gonna show in Finder just to see. No, I don't have the playlist. So you say NS allows arbitrary loads. It's probably the easiest for the purpose of a demo. Here they say that it's going to be ignored, but maybe on the simulator it's not going to be ignored. So check the info tab. So here, info, perfect. Do I see it somewhere or do I need to add a key? Bundle name, application supports, no. So I guess that's when I need to find the name of the parent key. So yes, I will need to add a key. If someone has the name of the key I need to add, I would love to know which it is. Okay, so it's NS allows arbitrary loads and then a value of true. Okay, so app transport security. All right. Let's go back to here. How do I add a key? It's just like that. So app. No. What did what did I break? I think I broke something, of course. I think it's here. So app transport security policy. Okay, perfect. And so now NS allows arbitrary loads. Okay, so inside of this allows arbitrary loads. Okay, and then I'm going to do yes. Hopefully I've set it correctly. We'll see. Let's go back to the code and we'll see who is going to run. That was a little unexpected difficulty. So we need to add this code. It's interesting. We are observing here. We're using the capture list. So we are doing this to capture the count. Okay. Oh, yes. So what we do is that we capture the count at the time where the effect is created. Because I guess potentially we could have several actions that run in a row. Each of them change the count, but the actions are run, the effects are run slightly later. So by doing this, we make sure that we do have the value of the count at the time where the effect is created and not at the time where the effect is run. Okay, and then inside I have this code. So like that. So for now, we make the network call, we parse the fact, and we still haven't sent it back into the system. Is there any guideline on how to test unit test with TCA? I think it's the next chapter, so we're going to get to it soon. And I see a question for Stefan in the chat, so I will let Stefan answer. Okay. And then, so here we cannot do states fact, does fact equal fact. It's the same problem that we would have in SwiftUI if it wasn't for the addState property wrapper, because you're not allowed to modify the in-out parameter in code that changes concurrently. So it might not be the exact same issue than there would be in SwiftUI if you didn't have addState to change like the state of a view inside the action of a button, for instance. But it's a similar problem. And so I guess the way we will solve it will be by sending a new action with the fact as data of the action. So let's see. Maybe I should have read step 3. So, however, it is not possible to then mutate the state.fact in the effect after fetching the data from the network. This is strictly enforced by the compiler since sendable closures cannot capture in-out state. So it's not directly a question of... it's not exactly the same thing than with SwiftUI, but it's similar. This is showing how the library chooses to separate the nice, simple, and pure state mutation that reducers perform from the messy, complex effects. So we see that there is like the separation that TCA makes between some simple side effects and some more complex one aligns with some rules enforced by the compiler, which is I was about to say which is a nice thing, but it doesn't say like a lot, but it means that there is really like this separation is made at a place that makes sense because the compiler is also making the separation at the same place. And it shows that there is an added difficulty into handling this kind of side effects because the compiler also needs to restrain the way we deal with them because it has consequences. So step 4, in order for us to feed information from the effect back into our reducer, we need to introduce another action called fact response. And it will have an associated value, and it will have an associated value of the string that is fetched from the network. Then we can send that action in the effect after performing the asynchronous work, and we can handle the new action by flipping the isLoading back to false and updating the fact state. So the loop is complete once we've done this. So we have a new case called fact response. with an associated value of type string. And so now that we have the fact, we're going to send a fact response with that fact. And of course, we need to add also, so this is async. So I need to mark it with await. Interesting that that this is async, but I guess maybe it's an await that is, maybe it's more an await linked to actor isolation, in the sense that, let me open send. So it's a yes. It's because send is annotated with @main_actor. So this await is actor isolation related, and it's here because this is probably running on a background thread. I mean, we hope that the network call is running on a background thread. So is the decoding, because it can potentially be costly, and we need to switch back to the main thread before we update the view. Hence, this await that allows us, that gives us the permission to await for a switch to the main actor context. All right, let's get back to it. So here we have the fact response, where we have the fact available. So let's write here. So case let fact no, I wrote it. Yes, it's here. I'm supposed to write. I was one curly brace too far away. So fact response, and we have the fact here. And so we will do state.isLoading. Cannot find, I think it's just like that. State.isLoading equal false, and state.fact equal fact. So the value, oh, I forgot the let. That's why it wasn't happy. Let's see if it builds. And I return no action, because there is no effect, to be run once we've gotten the response. But it's nice that we could also like send something else. So this would be kind of like the equivalent of a flat map in a way in Combine, where you want to make a second asynchronous operation after a first one has completed. I see. So Stefan, you're saying await send is due to actor isolation. Yep. If the effect were @main actor, then the await could be skipped. Indeed, because then the compiler wouldn't enforce the potential switch to another actor. And then you were answering regarding the README for the motivation for TCA. Perfect. Thank you for answering this question. Okay, let's get back to the tutorial. So did I write this part? I think I did. I even wrote the code. And there is a warning that says, currently we are ignoring any error that can be thrown by URL session. That's true. And the way we ignore it is kind of like, can be deceiving, because we do have a try, but the try is done inside a task, and then the task will simply disregard the error. So we have a try that kind of gives us the false sense of security that there is a catch somewhere, and there might be a catch somewhere, but it's just like empty. So in a more complete application, you would want to leverage task result to have errors fed back into the reducer so that you can react appropriately. And I guess maybe either you would have a result, so instead of passing fact response just a fact, you would have a result, which would be either a fact or an error. It could be a possibility. Or maybe have a separate action for when an error happens. But from what I've read, I guess the way to do it would be to have a single action fact response, and then have a result for the associated value that could be either the fact, the string, or an error. And if you ignore the error, you will get a purple runtime warning in Xcode at least. Oh, that's nice. I didn't know that. You're saying also, which isn't true of usual tasks, but we added that diagnostic to TCA's effect. Okay, that's why I didn't know that, because by default, indeed, a task will ignore its error, and it does it in a way that is slightly deceiving. And you're saying, Ibrahim, that you can write also catch to catch the error. okay, I haven't tried it, but you're saying we could catch the error like that. I think I'm going to stick to the tutorial for now. I'm thinking like, do I want to try it? But I see time is advancing, so I'm going to stick to the tutorial for now. So step 5. We can now run the application in the simulator or in a preview and see that the feature works as we expect. We can count up to a number, tap the fact button, and a moment later, a fact will be displayed at the bottom of the UI. So let's see if it works. Remember that I had to change the playlist and I'm not sure I did it correctly, so we'll see what's going to happen. So for instance, we have 3, fact, we see the loader. 3 is the number of spatial dimension we perceive our universe to have. Perfect. So everything worked. Woo, amazing. And we have also the console output we can see. Now it's getting more complex because we can see, for instance, that only is loading has changed. So now we can see what Stefan was saying as the minus and plus. So they are really like about showing a diff because these properties have not changed. So they have neither a minus or a plus. And then is loading as a minus to show what was removed from the state in a way, or the previous value, and a plus for the new value. So this shows us a great example to understand how to interpret these minus and plus signs. Great, let's get back to the tutorial. So section 3, managing a timer. Network requests are probably one of the most common types of side effects, but they are not the only kind. Let's add a new bit of functionality to our counter feature. We will add another button that, when tapped, starts a second repeating timer, and for each tick, we will increment the states count by 1. So we will start with the view layer, just as we did before. We will add a button that either displays start timer or stop timer, depending on some is timer running state. And when tapped, we will send a toggle timer button tapped action. That's all it takes for the view. So adding this button right here, it sends the action toggle timer button tapped. It makes sense, right? Because the timer, you can start it and stop it, and you need one button for this. So going to the view. So I guess this might be the point where in a real app you would like to start separate the view and the feature into files of their own. Okay, so it was added just below, just above the fact. I'm doing the same thing here. Note the isTimer running state and toggle timer button action do not exist yet, just like before. So nothing new here. Next, we will update the reducer by adding the isTimer running state, a new toggle, and a new toggle timer button tapped action, and stubbing in the basics of the logic for the new action. We know we will want to execute some asynchronous work, in particular a timer, so we'll have gone ahead and opened up a run effect. Okay, so going back to the feature, so I add a new state which is timer running. Yes, is timer running. Timer takes only 1M, and I set it to false, and then the action toggle timer button tapped. So case toggle timer button tapped. Perfect. And now we need to deal with this action. So let's add a case for it. So toggle timer button tapped. And what are we gonna do here? We're gonna do first state is timer running dot toggle. So if it's true, it becomes false. If it was false, it becomes true. And then we're going to return a run effect, and we just have to write the code inside of it. So inside the run effect, we can emulate a very crude timer by starting an infinite while loop and sleeping for 1 second inside the loop. This is not the best way to construct a timer, as it allows for drift to occur, but it will be fine for our purposes right now. So I'm going to just copy paste. It's going to be a bit simpler. Fix indentation. So while true, we sleep for 1 second, and then probably after 1 second, we do something in order to send something back to the reducer. You can see that I use the word send in natural language, which gives a hint that the naming is pretty good. Okay. Okay, so I'm at step 4. In order to react to each timer tick in the reducer, we need to introduce a new action, timer tick, that will be sent after each task.sleep, and it's in that action we will increment the state count. So a new action, we call it timer tick. So here we will send timer tick. You can see I do it after the sleep. This way I don't send it immediately on the first tap, so it emulates how a real timer would work. You tap and only after 1 second has elapsed does it send the first tick. And of course I need to deal with this new case. So timer tick. This one, so we already had the fact response, which was an action feeding back data. This one had an associated value. This one doesn't, because it's just going to increment the counter. And here we start to get to the point where you see I'm starting to duplicate code. I need to put the fact back to nil, for instance. So we'll see if the tutorial has some example on how to factorize some code, but here it's definitely the kind of point where you would probably want to factorize code a bit more. So, okay, and I return none because there is no effect following this one. So, however, there is a bug. If we tap the start timer button to start the timer and then tap stop timer, we will see that the timer did not stop. So let's see if it's indeed the case. But it seems true because we have no code to stop the timer, to stop it. So start, stop. Okay, it keeps going forever. So how do we fix this? To fix the bug, we can leverage a powerful feature of the composable architecture known as effect cancellation. We can mark any effect as cancelable using the cancelable ID cancel in flight method by providing an ID, and then at a later time we can cancel that effect using ID. Okay. So here, we're gonna say if is timer running, then we return the run, else we cancel. Okay. So in the action toggle timer button tap, when someone taps the button, we want to first toggle it, and then we're gonna do if state is timer running. So if it has become true, it means that we need to start the timer. So we move this right here, and in the else we will stop the timer. Okay. And I just need to create the ID, so this cancel ID dot timer. So does it say where it's created? Yes, it's another enum where we have the cancel IDs. So I'm going to put it here, for instance. And so here I'm gonna do cancel. We'll see just after what does cancel in flight does. And so the cancel ID, so it's just some ID I can pass to say, hey, when you receive this for a cancellation, you cancel this task. So it's just a way to give it an ID. And so here I'm going to cancel it. And to cancel it, I need to call something on the state, or maybe on something else. No, I just return. So it's another type that I can return. I can return. Oh, it's interesting. We just done none and run, but you can see there are other. We saw none and run. We saw publisher at some point when we look at the code, but there is also merge. So I guess if we want to run several actions in parallel, concatenate if we want to do them one after the other. So we can see we have the primitives to also compose effects together. And here we're gonna want to cancel and to cancel ID.timer. Let's see what the in-flight means. Determines if any in-flight effect with the same identifier should be cancelled before starting this new one. So what does cancel in flight determines if any in-flight effect with the same identifier should be cancelled before starting this new. So maybe it's like if you have already sent a cancel and it hasn't finish to cancel, what do you do? Maybe it's that. I'm not sure. Okay, at least it should be working now. So let's run the app again and let's see what's gonna happen. So I start the timer, and when I stop it, it does stop. Perfect. I restart it. It restarts, and it does stop. Okay, perfect. So I'm not sure what the cancel in flight means actually. Stephen, if you're still here and you have a better answer, please feel free to help me. Okay. So step 6, now the feature works as we expect. We can start the timer, wait a few seconds to see it count up, and then we can stop the timer. This shows how to manage a long-living effect, including how to cancel effects, which is something important and not necessarily like trivial. I remember a few years ago seeing a talk about Promise Kit and how challenging it could have been to it was to actually like cancel some promises in the call chain. So Stefan, you're saying cancel in flight will cancel any effect that is already in flight with the same ID. Okay, so maybe what I don't understand is that by default, cancel in. Oh, okay. I guess I get it. It's that if at the time where I'm creating this, there is already a cancellation in flight, then it will cancel the new task I've created even before it had a chance to start. Maybe that's it. So Nico, you were saying, you want to make it so it's easier to read. Cancel in flight probably stops any other task running with the same ID before starting a new task, i.e. there will always be only one task with the same ID. It could be handy for a debouncing effect. Okay, so cancel in flight. Okay, so it's like if there is already. Okay, so if there is only at maximum one with the same ID that is running. Okay, and so now what you're saying, Stefan, makes sense for a debouncing effect where you start a timer for 300 milliseconds, and if the user does a new action, you want to reset that timer, and so you cancel the one that is already in flight and you restart a new one. Okay, that makes sense because the cancel in flight is from the point of the cancelable and not the cancellation. I think that's the part where I was a bit confused. But indeed, cancel in flight is an argument of cancelable, so here, and not of the cancel operation itself. Okay, let's get back to our tutorial. I think we finished the second chapter, so now it's testing. From what I understand, one of the big advantages of TCA. So let's go into testing. This is the longer one. I think I'm going to be a little bit longer than I wanted, but I don't want to stop. It's interesting. It's going very well, and I see there is still a good amount of people watching, so let's keep going. So in this chapter, we're going to learn how to write tests for the counter built in the previous tutorial, including how to assert against state changes and how effects execute and feed data back into the system. So section 1, testing state changes. The only thing that needs to be tested for features built in the composable architectures is the reducer. And that comes down to testing two things: how state mutates when actions are sent, and how effects are executed and feed their data back into the reducer. State changes are by far the easiest part to test in the composable architecture, since reducers form a pure function. If you're not familiar, a pure function means that it only depends on its input. So for the same input, it will always produce the same output, and it's not going to run any side effect inside its body. All you need to do is feed a piece of state and an action to the reducer and then assert on how the state changed. And because the state argument is in-out, we can see it as kind of like a hidden return value of the function. But the composable architecture makes an easy process even easier thanks to the test store. So what you mentioned in the chat, I think, Stephen, the test store is a testable runtime for your feature that monitors everything happening inside the system as you send actions, making it possible for you to write simple assertions. And when your assertion fails, it provides a nicely formatted failure message. Okay, so now we are writing tests. So let's write a test for the very simple incrementing and decrementing behavior in our counter feature. We will start by creating a counter feature test.swift file with some basic scaffolding in place for the test. So I'm glad I've created my testing target when I created my project. So I'm gonna go into this one, so not the UI tests, creating a new Swift file, counter features test, and let's see. I'm just going to copy and paste. It will be easier. So what do we have? We import XCTest, makes sense for a test. We import the composable architecture, so maybe I will need to also add it here as a framework that is linked. So I'm going to add it, composable architecture, perfect. And then we have the class counter features test, which is the XCTest case, and test counter. It's async. Tests are allowed to be async. We're good. So let's write a test. No, it's what I've just written. Note, we are going to preemptively make the test method async because the testing tools of the composable architecture do make use of asynchrony. So step 2. Next, we will create a test store, which is a tool that makes it easy to assert on how the behavior of your features changes as actions are sent into the system. You create a test store in the same way you create a store by providing some initial state to start the feature in and providing a trailing closure to describe the reducer that will be powering the feature. So let's create this store. So it's gonna be a test store. It takes some initial state, which is counter feature.state. Counter feature.state. Maybe I also need to import my app. I think that's what I forgot to do. So I need to do an @testable import of my app. If you're not sure what @testable does, it allows you to access internal symbols inside this module from the test, even though you're not supposed to access internal symbols from a Swift package, but this makes it possible because for a test, it's very useful. And then the trailing closure here. And so in the trailing closure, I guess I'm going to pass in just my counter feature like that. Is it the right thing to do? Yes, perfect. Step 3, then we can start sending actions into the store in order to emulate something the user is doing. For example, we can emulate tapping the increment button and then the decrement button. So once again, we can see that the naming makes it quite easy to write the code. So let's do await store.send increment and then await store.send decrement. Perfect. Note, the send method on the test store is async because most features involve asynchronous side effects, and the test store using the async context to track those effects. So step 4, run the test by tapping Command U or clicking the test diamond next to test method. Unfortunately, you will find that the test fails. This is because each time you send an action to a test store, you must also describe exactly how the state changes after that action is sent. The library also helpfully shows you a detailed failure message showing you exactly how state differed from what you expected, the line with the minus with the actual value, the lines with the plus. So it fails because the state changed, but we didn't say it was expected to change. So I guess the way we write the test is by saying all the change we expect, and then if something outside of this expected range happens, the test fails. Which is interesting. In a way, it kind of, not fully, but it kind of reminds me of property-based testing, where you define a property that should hold true for all possible actions. Here we say that when we send this, we should have, it's not exactly the same thing as property-based testing because we only send the same action. So it's not like if we are sending like different things, but there is this idea of describing what is expected. And if anything outside of that range happens, then we consider it a test failure. So let's run the test to see that we get what we're supposed to get. So it probably take a bit of time to build the first time. Build failed. Why? I don't like this kind of errors. Undefined symbol. Yes. Can I get something a bit better? Maybe if I go. So here, and I show all issues and all. So it says could not find or use AutoLink framework. Okay. I'm gonna try to just do a normal build. This one succeeds, and if I do a test, the build fails, and I get the same error in that case. I'm gonna do a clean because you never know. And then I will, if it doesn't work, I will just have a look in the project to see what could be missing. I've added TCA here. And it's not the UI test, it's the normal test. Maybe I shouldn't link TCA again. So maybe it was a mistake. I did it like by reflex, but maybe it was a mistake. I'm just waiting to see like if the build still fails. Okay, it still fails, so I'm going to just remove it. Okay, this time. So it was my mistake. Thank you for the help, Stephen. So, okay, now it's testing. We should see. Okay, I'm going to move the simulator out of the view because you don't need a. Okay, it's creating several simulators. I'm going to move both of them out of the view. Okay, so the tests are running, and normally I should see these errors that should tell me that it didn't expect the count to go from 0 to 1. It hasn't started the apps on the simulator for now. So we still need to wait a bit. Made a wrong move and I moved my picture, my Xcode. Sorry for that. Message in the chat. Carol, you're saying other nice thing about this test convention is making our test look like documentation of how the feature exactly works, and also while writing the action name like that is very helpful. Yes, totally agree with this remark. Okay, I need to give it permission. Let me move this to another screen. Okay, we get it. So state was not expected to change, but a change occurred. Okay, we get what was expected. Okay. And I think I tapped on Command U more than I should because it's running. Ah no, it's because it's running also the UI test. That's why. Okay. What I'm gonna do is that I'm gonna get rid of the UI test because I know I don't want to run them anyway. So I can get rid of them. All right. So let's get back to it. Let's go back to how do we fix the test. So to fix the test failures, we need to assert how the state changed after sending each action. And the test store makes this very ergonomic. You only need to provide a trailing closure to the send method. That closure is handed a mutable version of the state before the action was sent, and it's your job to mutate $0 so that it equals the state after the action is sent. So we need to basically, we are replicating, no, we're not replicating because we're not, I was about to say we're doing the same thing than in the feature, but no, because the feature says count plus equal 1, but here it says count equal 1. And the way it's written, this equal is kind of like if we are doing an equal, because then it will compare the state modified by the closure with the state modified by the action. So our closure here is doing the changes we expect the action to make, and then the tester will compare that the action did indeed make the same change than what we've made ourselves, and if it didn't, it will report a test failure. So it's the first time I see this syntax. This one I didn't know about it, or if I did, I had time to forget about it, and I really like it. I indeed think it's a very elegant way to describe it. So count equal 1, and then here $0 dot count equal 0. All right, let's rerun the test to see what's gonna happen. Okay, this time it passed. Perfect. So let's see what's next in the tutorial. Oh, we have a tip. So prefer to use absolute mutations such as count equal 1 rather than relative mutations such as count plus equal 1. Exactly the point I was mentioning before. The former is a stronger assertion that proves you know the exact state your feature is in rather than merely what transformation was applied to your state. Because that's a very good thing. Because if you do count plus equal 1, then you are asserting, what you are asserting is that you have successfully duplicated the implementation that you have in the feature. And when you do equal 1, you are asserting that the implementation in the feature, given this action and initial state, does produce this result. So indeed, it's stronger because the other implementation is just going to fail if you change the code in one place but not in the other. Whereas the other one, it will hopefully describe expected behavior, and so it will fail if the feature deviates from this expected behavior. And it's a very easy mistake to make, and honestly, I might have made it by mistake without thinking about it. So it's a good thing that it's been highlighted. Good question. How would you test state properties that aren't equatable? That's a good question. Actually, I'm not sure if I'm gonna look to see if there is a requirement, because here we have state. Is state supposed to be is it supposed to be equatable or not? I think, yeah, it's supposed to be equatable. So I guess, and Stefan, if you're still here, you can confirm. I guess what's happening is that the equatability of the state is used to determine whether the expected state is the same than the actual state. And then on a second time, to generate the diff, then there is some reflexivity with mirrors that is used in order to know which property exactly generated the issue. Let me know if I'm correct. But indeed, for testing, state must be equatable, which doesn't mean that all of its subproperties are actually equatable. By default, if you conform to equatable and all your properties are equatable, then you get the implementation of equatable by default, so the equal operator. But it's possible to have some properties which are not equatable and to define your own equal operator and simply either ignore these properties or just look at an ID. I mean, do something different. So there is room for a bit of subtlety here. I hope that answers your question. Let me get back to the tutorial. So now the test passes, as we've seen, and so proves that the incrementing and decrementing logic does work as expected. However, the increment and decrement logic is some of the simplest in our feature. In more real-world features, the logic will be a lot more complex and you will have to do more work to assert on how state changes. But luckily, doing so can be ergonomic, and test failure messages are user-friendly thanks to the test store. Okay, so Stefan, you are confident that I got it correctly. Testing the test store requires equatability of state, but luckily that is typically easy to do for structs and enum. And I guess I'm thinking like typically like an example. It's like I don't know, like you're doing image generation and you need to compare UI images, but what you want to compare is that the pixels are the same, then maybe in that case you need some custom equatability conformance, because you don't just want to you don't just want to test that it's the same. You don't want to test that it's the same image in memory, but you want to test that the two images contain the same thing. But it's a edge case, and most of the time you will just test the name of the image, because most apps are not generating images on the fly. I work on image editing apps, so I'm a bit biased on that end, but I recognize it's not the case of all apps that they need to generate images on the fly. And Prafamesh, you're saying I should be able to use a closure that returns bool that works like XCT assert true, right? What do you mean by that exactly? I'm not sure. You would like to use a closure that returns a bool. So you mean the closure that we pass here, for instance? If you can explain a bit more, it might help me understand it, because I'm not sure I fully grasp it for now. So section 2, we are moving on to the part where we are testing the side effects. So we just tested one of the most important responsibilities of the reducer, and that is how it mutates states when it processes an action. The next important responsibility of a reducer is the effects it returns that are then processed by the store. Writing tests against side effects takes a lot more work, since you typically have to control your dependency on external systems and then provide test-friendly versions of those dependencies for test. For instance, for the network call, you need to mock the return of the network call. So let's start by testing the timer functionality of our feature, which turned out to be a little easier to test than the network request for fetching a number fact. Oh, you make a very good point, Ryan. You say it seems like there will be a lot of duplicated code in our test if we have to mention all the changes to the state of our test to pass. That's true. That with the syntax where we do the mutation, we only mention what is expected to change, and from that we can infer that the rest is expected not to change. But indeed it makes the code easier to write, because I guess in the majority of cases there will be less state mutated than there will be state that stays unchanged by an action being applied. So that's a very good point. Thank you for making it. And then you explain the rise that then it would become cumbersome to write time after time, and also it would be very error prone if there wasn't a mechanism to make sure that you had written an assert for every property. That's also the great thing about it, is that you say what should change, and from that the tester can assume that the rest isn't supposed to change. Whereas if you were to write everything exhaustively, you need a mechanism to let you know if you've forgotten something. Otherwise, you might have things that slip through the cracks without you being aware of it. Okay, so apparently you can also turn it off and only assert what you're interested on. Interesting. Even though I guess it could make sense for like some performance situations. And you meant it more as an open speculation than a question. Okay, thank you. And Stefan, you're saying there is a non-exhaustive mode of tester that allows you to only mutate state you care about. It's a give or take situation. It's good that we have the choice. Okay, so this non-exhaustive mode of tester. So I'm still trying to finish to wrap my head around it. Oh, okay, so like I guess by default, okay, I think I get it. So in both cases, in both the exhaustive and non-exhaustive mode, you still write the mutation that you expect. So like the ones that you can see here, that happens in both cases. But then in the exhaustive mode, it's going to assume that any change outside of the ones you specified is a failure, whereas in the non-exhaustive mode, changes outside the property that you have specified will be ignored and not considered a failure. Let me know if I've gotten it right. And it's store exhaustivity equal off. So let me try and do it. So if I were to do store.exhaustivity equals false, and for instance, let me just comment this line. Should the test still be passing now? Actually, I need to remove the closure for it to build. Oh, it's okay, it's off. Okay, so the test succeeds in the sense that I haven't written anything that contradicts the changes that happened. I guess, I guess, and I'll let you confirm, Stefan. But when you turn exhaustivity to off, then it uses something else than equatable, because with equatable you only get like you cannot pick and choose which property has changed. So I guess when you turn it off, it must use another way to compare, maybe mirrors or thing like that. Because with equatable, you can know whether the state as a whole has changed, but you cannot do this for each of the property. If you have the answer, I would love to know it. And let me put back the code like it was. And you can also show the skip assertions to see, like in the console, I guess, if something has still changed. You can still get some like light warning. It doesn't fail the test, but it shows you that something happened. That's also a nice option. Okay, so we were at testing effects. So let's get the scaffolding of a new test into place by creating a new async test method and constructing a tester. So this time we create a func test timer. All right. No, just like that. Oh, so if you do off, it will compare against. If you do off, it will compare against the after value instead of the before value. Okay. Okay, that makes sense. That makes sense. And so since it was off, it compared, and so it will catch bad mutations. So if I do off, it will compare against the after value instead of the okay, so here, since I didn't do anything, and it shows the skips in Xcode. That's nice. And just I'm trying to wrap my head around it. So when I disabled exhaustivity, I had also removed the $0.count equal 1, which means that so store.send.increment would have incremented the count. And so why did the test succeed? Because I didn't say that it would be equal to 1. Oh, it will compare against the after value. Okay, so since it compares against the after value, and since I didn't make any change in the closure, then it compared the after value with itself. I think I've got it. Okay. Let's go back to testing side effects. So I've added the test timer method right here. Okay, I think I've got it this time. I think I've got it. Just displaying the command. So with exhaustivity on, it hands you the before state to mutate into the after. And with exhaustivity off, it hands you the after state. Okay. Oh, okay. So I guess, so let me know if if I get it correctly. So if I do exhaustivity equal off, then here, I guess what I should have written was not this, but rather xct assert equal $0.count and then 1. Let me know if I get this correctly. And maybe this also links with the point you were making, Prathamesh, that disclosure will return a boolean. And if I make one that would fail, okay, this one has failed. So from what I see, I think I've got it correctly. Let me know if that's indeed the case. I'm gonna let the change into test counter for now, but we can go back to focusing on test timer. Okay, and apparently I can still do, so I can still do $0.count equal 1. Okay, and it will, okay, I do that, and then it will fail if I do equal 2. Okay, so I can, if I get it correctly, is that I can write this code using this syntax, but because exhaustivity is off, writing this is equivalent to writing this, because I still need to write myself, like everything that is not asserted is not tested. That's how I understand it, which would make sense with exhaustivity off. So like this, same thing. Let me know if this is correct. And let's go back to the timer. So we want to test the flow of the user starting the timer, waiting a few seconds to see the count go up, and then the user stopping the timer. This can be done by emulating the user starting the timer by sending the toggle timer button tapped action, and we can even assert on how state changes since we know the isTimer running state should flip to true. So let's try and do this. So we're going to send the action that starts the side effect. Let's also reindent. So we send the action toggle timer button tapped, and this action, it flips, it toggles the boolean, and it also creates the action, the effect. The effect. So for now, I'm only testing the mutation, but not the effect itself. But I guess we're going to do it just after. However, if we run this test, we get a failure. It tells us that the test ended, but that an effect was still running. So let's try to reproduce. An effect returned for this action is still running. It must complete before the end of the test. Okay. So that makes sense because any unfinished effect or unhandled is considered a test failure. So let's see how to handle this effect. So this is a failure because the tester forces you to assert on how your entire feature evolves over time, including effects. In this case, the tester is forcing that all effects that were started in the test finish before the test is over. This can help you catch bugs, such as if you didn't know an effect was running and it emitted actions back into the system that you did not expect, or if your state mutations from those actions had bugs. So this is a very good failure to have, and is one of the many ways the composable architecture can help us catch problems in our code. So to get the test to pass, we simply have to emulate the user toggling the timer again by sending the toggle timer button action again. So it's basically duplicate this. This time we expect it to be false. And so it should succeed because the effect has finished because we canceled it. Okay. While this test does pass, it also isn't asserting on any of the timer behavior. We are only asserting that when we send toggle timer button tapped a second time, it does cancel the timer. We would like to assert that after some time, a timer tick action is sent into the system and causes the count to increment. This can be done by using the receive method on tester to assert that you receive an action and describe how state mutates upon receiving that action. What's really nice is that we can see that the flow of the test reads from top to bottom. So that makes the test very easy to read. We are not nesting closures or doing expectation or this kind of thing. So here we do await store dot receive. So we want to receive the action timer tick. Okay. And we also need to give a timeout. Do we have to or not? Not necessarily. So there is a value by default. And then just like for send, we want to test that when this new action is received, it mutates the state in the expected way. So here it would be count equal 1. Yes, and not plus equal 1. So when you read the test, it says send this action to the store, then wait until the action timer tick is received, which should and this action should be emitted if the timer is working as expected, and then send toggle timer button tapped again. And if timer tick is not emitted by the timeout, then I guess the test is considered a failure. So let's try and run this. So it succeeds. And we could probably add a few more if we wanted, and this time do 2 and then 3. You can see it takes a bit longer, which means that the test is working as expected because it waits 3 seconds now and it's still succeeding. Perfect. Section 3, testing network requests. So network requests are probably the most common kind of side effect in an application, since most often some external server holds your user's data. Testing features that make network requests can be difficult because making requests can be slow, can depend on your network connectivity or the servers, and there's no way to predict what kind of data will be sent back from the server. Let's try writing a test for the number fact behavior in a naive way and see what goes wrong. So let's see. So we are writing a new test. So test number fact. So we add a new test method to counter feature test Swift for testing the number fact behavior. Also go ahead and get some scaffolding into place for the tester. So I'm adding a new test method right here, fixing the indentation. Okay. For the test, we want to emulate the flow of the user tapping the fact button, seeing the progress indicator, and then sometime later, the fact is fed back into the system. So first, we emulate the user tapping the button by sending the fact button tapped action, and we can already assert that isLoading must be flipped to true. So we're gonna get the store. We do await store.send fact button tapped, and so isLoading should be true. I wanted to say something and I forgotten. Yes, I wanted to say that this says that it tests that the loader is displayed on the screen. To be perfectly exact, it tests that isLoading becomes true. We could also have a bug in the view that makes it that isLoading is not matched to the loader appearing, and this will not catch it. So it only tests the logic, but now not how SwiftUI reads that logic. You would still need some kind of UI test for that part. Unfortunately, if we run the test, we see it fails. This shouldn't be too surprising based on what we have learned before, because there is an effect still running. The tester forces us to assert on how all effects execute, and since the network request has not yet finished, we are getting a failure. To fix the test, we need to wait for the network request to finish and receive the fact response action. But then the question is, how do we assert on the fact returned from the server? Each time we ask for a fact from the server, it may send us something different. So, yes, because we could say so await store.send store.receive rather. So receive fact response and then a timeout of 1 second. Is there a default value for a timeout? I'm looking to see what happens if I don't pass in a timeout. I should just command click here, it will be easier. So here, we just pass it here. Okay. What do we do here with the timeout? We just pass it here. Okay, otherwise there is a default timeout. Okay. But I guess it's it's way long. It's a bit longer than 1 second, maybe. Okay, let me just go back to the tutorial. So yes, how do we test the fact because we don't know what the network will return? So if we run the test, we'll see the test fails because we received a fact from the server we could not have possibly predicted. So in the example, it does two things. So it tests that is loading is back to false. And then what is the fact? We don't know. And so if I run the test, it should fail here. So a state change does not match expectations. And so you can see we were saying question mark for the fact, and then we got 0 is the atomic number of the theoretical element tetraneutron. So what we are seeing here is that there is no way to test this behavior. The server will send back a different fact each time. And even if we could predict the data sent back from the server, it still would not be ideal because our tests will become slow and flaky since they require internet connectivity and uptime of an external server. So how can we do better? How can we maybe inject a mocked dependency? So section 4 is about controlling dependency. So now we see the problem with using uncontrolled dependency in our feature code. It makes our code hard to test and can make tests take a long time to run or become flaky. So uncontrolled dependency, here it refers to the fact that we used URL session just by calling URL session.shared, so using a singleton. For these reasons and more, it is highly encouraged for you to control your dependency on external systems. So there is a dependencies in the doc for more information. The composer architecture comes with a complete set of tools for controlling and propagating dependencies throughout an application. So let's try and create a proper dependency for our number fact. So let's start by creating a new file numberFact client.swift and import the composer architecture. This is going to give us access to the tools to control any dependency in your feature. So this we're going to do it in the app, I would expect. So not here. Better. So here we import the composable architecture. What do we do next? The first step to controlling your dependency is to model an interface that abstracts the dependency. In this case, a single async throwing endpoint that takes an integer and returns a string. This will allow you to use a live version of the dependency when running your feature in simulators and devices, but you can use a more controlled version during tests. Okay, so let me add this. So basically, what we need is a function that takes an int and returns a string, and that function can await and can throw. Tip: while protocols are by far the most popular way of abstracting dependency interfaces, they are not the only way. We prefer to use structs with mutable properties to represent the interface and then construct values of the struct to represent conformances. You can use protocols for your dependencies if you so wish, but if you are interested in learning more about the struct style, see our series of videos for more information. I will let you check out these videos from point 3 if you are interested in learning more. So step 3, next you need to register your dependency with the library, which requires 2 steps. First, you confirm the client to the dependency key protocol, which requires you to provide a live value. This is the value used when your feature is run in simulators and device, and it's the place where it's appropriate to make live network requests. So if you've used the environment in SwiftUI, this reminds me a lot of environment keys in SwiftUI. And Stephen, I guess you can confirm, but it might have been an inspiration for the design. So we need to import Foundation because what we want to use for the live version is URL session, which is in Foundation. I see you're saying Pradamesh. I'm gonna call it a night there. Thanks for the stream, Vincent, and thanks Stephen for hanging out there and commenting. Thank you for watching up until now, and don't worry. As always, the replay is available as soon as the live is over. So let's add the extension of numberFact client to confirm to dependency key, which, as I was saying, reminds me a lot of environment key in SwiftUI, except that environment key in SwiftUI as a default value here we have a live value, And so the live value is going to be this number fact client. So actually here it's just like if we had written this. And so fetch, we are given a number and we do the network call. So it's exactly the code that was in line inside the reducer up until now. So the uncontrolled dependency. Okay, what's the next step? We have a note. Technically, the dependency management system in the Composer architecture is provided by another library of our Swift dependencies. We split that library out of the Composer architecture once it became clear that it could be useful even in vanilla SwiftUI and UIKit applications, which makes sense. Dependencies is designed to be like environments. I got it right. Nice. And Reducer is designed to be kind of like Vue. We like to design TCA to be approachable to folks familiar with SwiftUI. Yeah, we saw that the Reducer has this body also, which is a nice trick that I didn't expect to see. But what's nice is that I was at NS Spain, I think it was in 2018, when you gave the talk How to Control the World. And if people are interested, this talk, I always see it as like the inception point of TCA, because, or at least the dependencies part, because the ideas were in this talk. So it's nice to see how this idea has evolved over the years. Okay. A good question. Is it best practice made by Apple or did you miss something bigger? So it's not Apple. This library is not made by Apple. It's made by the community. And the documentation, the tutorial looks like Apple's tutorial because Apple has made their tutorial platform available. Like you can create this kind of tutorials yourself. So that's why it looks like something from Apple, but it's not from Apple, it's from the community. Very good question. Thank you for asking it. So where was I? Yes, I was at step 4. The second step to registering the dependency with the library is to add a compute property to dependency values with a getter and a setter. This is what allows the syntax add dependency / number fact in the reducer. So definitely the same thing than with environment key. So if you're using SwiftUI, as Stephen said, you should not be lost. So dependency values is here. So we have number fact, and we have exactly the same approach than environment key uses, than environment values uses in SwiftUI. Note, registering a dependency with the library is not unlike registering an environment value with SwiftUI. Actually, it was written, it was spelled out just after, which requires conforming to environment key to provide a default value and extending environment values to provide a complete property. And since I know that there are macros to write this for you with environment key, maybe you could even go further and create macros that would generate part of this code for you. That is all it takes to put a controllable interface in front of your dependency. With that little bit of upfront work, you can start by using the dependency in your features and, most importantly, start using test-friendly versions of the dependency in tests. So step 5, we go back to counter featured Swift and we add a new dependency using the @dependency property wrapper, but this time for the number fact client. Then in the effect, return from the fact button tapped, use the number fact dependency to load the fact rather than reaching out to URL session to make a live network request. Okay, and we can see that the clock, it also uses a continuous clock, which I think we haven't used up until now. So I won't make that change just in order to not break everything. So here we are having the number fact. And so this code here can be removed. And here we can do let fact equal number fact. And we give it the count as its argument. Cannot call value, or it's because it's fetch. And also it's try await. Forgot that part. So let's just run the app to see if it still runs correctly. Okay, that part works, but I haven't changed it. That one still works. Perfect. And 1 is the number of moons orbiting Earth. I think this is the correct information. Perfect. Okay, let's go back. So I've made that change. So without making any change to the test, let's run it again. So let's see what's going to happen. So let's run this test again. So it's testing. Build succeed. So here we get another test failure that says add dependency number fact has no test implementation but was accessed from a test context. So it tells us that we need to implement the test implementation. So it's nice to have this warning. This way, like if we forget to do it, we have a failure by default. So the test fails with the same messages, but there is a new one. It tells us that we are using a live dependency in our test without overriding it. This is a fantastic failure to get because it notifies us whenever you may be accidentally making a network request or writing something to disk or tracking analytics in a test when you don't mean to. So we definitely do not want to make a live network request in our test. So let's fix this, let's fix it. And this will make our test pass immediately and deterministically 100% of the time. We are going to make one small change that instantly makes the feature testable. So when we create a store, we will pass in a second closure called with dependencies. So we override dependencies on the tester by opening the with dependency trailing closure. This closure is passed as an argument that represents the current dependencies, and you can mutate it to change the dependencies however you want. In particular, we will override the number fact.fetch endpoint immediately to return a hard-coded string. Notice that there is no true async or request work being performed in this test or mocked version of the endpoint. And what's nice is that we can only override what we need, and the rest, as long as we don't use it, we don't need to override it in the test. So here we're going to say with dependencies. And so here we do $0 dot number fact dot fetch, and then it's going to be equal. And so yeah, there are still curly braces because it's still a function, and it's a function that returns this string that says, okay, the number passed is a good number. This way we have a deterministic string being constructed given an integer. So now we just need to update the test. So here in that case, for instance, we would expect it to say, so fact button tapped, since it's going to be 0, it should say 0 is a good number. Did I make the right change? Yes. So now that we have overridden the number fact client to always return something predictable, we can drop the timeout from receive and properly assert on how state changes. So let's run the test one more time. This time the test is successful. Nice. That is all it takes to prepare your feature for testing. It does take a few upfront steps, but once done, you can immediately use the dependency in any feature. There are even more benefits to controlling dependencies beyond writing tests, such as running Xcode previews in a control environment and providing onboarding for your users that run your features in a sandbox so that you do not accidentally make changes to the outside world that you did not expect. And when you see it, you understand why they chose to put the dependencies part outside of TCA, because even if you don't use TCA, you probably should still use a form of dependency injection. And this is, I would say, a very good approach, and definitely like an interesting alternatives to other frameworks like Swinject, for instance. And there might be more modern one, or even just using the environment to inject stuff in SwiftUI. I think we have our own implementation of dependency management at work on the app I work on, but it's basically a simplified version of this. It doesn't cover as many use cases, but the gist of it is kind of the same thing. And it seems that did we cover everything? What is the next part? So yeah, the next part is about navigation. So we are where I wanted to stop. So I wanted it to last around 2 hours. It lasted 2 hours and 40 minutes. But let's see. We still have 23 people watching. So this might be a record-breaking live stream for my channel. So I'm really glad that I chose this topic, and I'm also glad that I picked it because I learned some more things, some new things this evening. There are stuff that I already knew, but I had seen it like maybe in a conference talk. And when you see content in a conference talk and you don't practice after, you tend to forget it pretty quickly. But I like what I've seen, and what I really like is the fact that even if I will probably not be using TCA tomorrow in my case because I'm working on an app that already has an established architecture, some of the design principles that TCA uses, I'm glad that I've seen them because I'm sure I can apply them in the code I'm going to write in the future. There are some very interesting design choices being made. There are some very clever use of features of Swift, like the dynamic member lookup subscript with a key path, the call as function, the generic type alias. So I think like it's interesting. This live stream is interesting whether you are going to use TCA or not, because in both cases, either you've learned how to use a new tool or you've learned some good design principles and design ideas that you can apply for your own code, for the own architecture that you're going to come up with. So I think we're getting near the end. So as always, thank you all for watching. A big thank you to the person who asked questions, made a remark in the chat, because it made it a great experience for me, and I'm sure some of the questions and remarks that you have asked, the people watching the replay will have the same, and so they will be very glad that you gave them a voice through the chat. A big thank you, Stephen, for being here this evening and answering the question. It was very valuable for me and even more for the audience. So thanks a lot for taking the time. And maybe I will do a part 2 about the navigation. We'll see. But I'm glad that we've covered the main key points of this architecture. And finally, like I mentioned, as with all of my live streams, a replay is available immediately after with the same link done for the live stream. So if you've enjoyed the live stream and you want to share it with your colleagues at work, you can just share them the link and they will be able to watch the live stream. That's all I wanted to say. It's almost 11 p.m. for me. I'm starting to get super tired, so I think I will go to bed soon. But thank you again for watching. See you next time. Bye-bye.